continuer. Je rappelle le président du jury. C'est un peu compliqué, je crois. En plus, il s'est fait un truc à la jambe. Ah oui? Ça fait une déchirure. Tu peux aller ça. C'est long à galère. C'est en glissant sur un truc, et c'est retenu.
Comme manquer des défis musculaires.
Oui, salut Olivier. Ok, super. Bon, bah, tout de suite. Ok, parfait. Ouais, tu le vois apparaître.
Est-ce que tu vas pas lire apparemment c'est quelqu'un à mettre, ça veut dire. C'est pas quelqu'un à mettre. C'est bon, c'est bon.
Eh ben,
Vérifie qu'il entend bien quand même.
ouais, je vais. Hello everyone. I will just ask the member of the jury to make sure they hear us correctly. So we're gathered today to attend the defense of Mr. Hugo de Blevec. The jury is made up of the following people. I will first start by the reviewer of your work, Olivier Santies. Olivier, can you hear us?
Yes, very well, thank you. Hello, everyone.
Andrea Pina. We have as examiner Anastasia. I forgot to say that Olivier is from INRIA Rennes, and Andrea from Lipsis, professor at Lipsis in Paris. We have Anastasia Volkova, who is chargée de recherche at INRIA Lyon. We have Camille Leroux. Camille, Anastasia, can you hear us?
Yes, very well, thanks.
Yeah, thanks.
Yeah,
Camille.
perfect.
Okay, he's maître de conférence at Bordeaux INP in Bordeaux. We have also Thomas Preutzer at AMD Dresden. Thomas, are you hearing us?
Yes, all good, thanks.
Yeah, thank you very much. We have Jacoba Petri-Koenig with also at AMD in Dublin. Jacoba, can you hear us?
Yes, I can. Thank you.
Yeah, thank you. And then we have the thesis direction with Mathieu Léonardon, that is maître de conférence at IMT Atlantique, and Mathieu Arzel, that is professor at IMT Atlantique. And so I have the honor of chairing this jury. I'm Frédéric Pétraud from professor at Université Grenoble. So, Mr. Blevec, you have 45 minutes to present your work.
Thank you, Mr. President of the jury, for the introduction. Thanks to all the members of the jury for attending. I am honored to have the opportunity to present to you some of the work that I did as part of my PhD on the joint design of deep neural networks. and FPGA dataflow architectures for semantic implementation with autonomous vehicles. So allow me to start with a brief introduction of the PhD subject and context. So this PhD thesis studies semantic segmentation, which is a machine vision task whose goal is to attribute labels to the pixel in an image or video and use this labelization to give a meaning and an understanding of the objects in the scene and the relationship. And use these informations to this understanding to infer decisions. So modern techniques use deep neural networks as the main revolve around the use of deep neural networks. And in the deep learning community, it's considered, so semantic segmentation is considered to be a rather challenging task, especially compared to more popular tasks like classification. And finds several applications, domains, including medical imaging, satellite imaging, agriculture, and lastly, autonomous driving. And this application in particular is the one that I focused on during my thesis. So to evaluate the performance of deep neural networks in semantic segmentation, we compute a metric called the intersection of a union, which is obtained as the ratio between the area of overlap between the ground truth and the prediction and the area of union. And so once we have the IU on each of the object class in the image or in the data set, we can compute the average between these classes and have this metric called the mean intersection of a union, which is the standard metric to evaluate the performance of deep neural semantic segmentation deep neural networks. In terms of data sets that can be used to train deep neural networks for autonomous driving applications, there are two major ones. The first one being CAMVID, which is like a rather small data set with 11 classes. And the second one is Cityscapes, much larger data set with high resolution images and 90 classes. And so Cityscape is really the baseline data set for training networks on semantic segmentation for urban scene understanding and autonomous driving. So this is the data set that we've focused or centered our research around. So the goal of the thesis was to study real-time semantic segmentation in low-power autonomous driving embedded systems. And so this goal is associated with several constraints. Since we're talking about real-time, we have a speed and timing constraint that we determine as being roughly a throughput at least 30 FPS to match the speed of cameras, and a latency that is in the tenth of millisecond of order of magnitude. And the power constraints can be translated into memory and computation constraints. It means that the network, the system that we want to embed must remain within a certain limit in terms of memory and computation footprints to be able to be embedded in low power hardware. There is a wide variety of deep learning models that are trained on cityscapes. And we find that there's a discrepancy between state-of-the-art models that only focus on having good semantic segmentation performance on the benchmark, which are the points in blue here, and what we call real-time models in red, which also includes metrics and evaluation on other aspects, like having a high enough throughput to be relevant for real-time inference. And we can see that in general, real-time models tend to have a lower performance on semantic segmentation in number of MIU, but also to have lesser number of parameters. And then one of the interesting questions when working on this topic is what in this wide variety, which model should we choose? Where do we want to land on this Pareto curve between semantic segmentation performances and model complexity, here represented in number of parameters? And before knowing which model to use, we must know which hardware device we want to use. So there's generally three main categories of hardware device that can be used to embed deep neural networks. The first one being what's called neural processors, which are application-specific system on chips, usually embedding special accelerator cores, like the tensor processing units from Google, for example. They have different development workflows that are specific to the manufacturer, and they display a very good, or probably the best power efficiency across all devices. But our previous experiences with it show that it's rather difficult to use them outside the specific use case. And also they don't offer a lot of opportunity to explore the design space and explore the trade-offs between hardware performances and MIU and all these kind of trade-offs. The second category is embedded GPUs. So they are highly parallel processors that are very efficient at accelerating the operations done in deep learning, in deep neural networks. And they have a great advantage of having very straightforward development flows thanks to the use of efficient compilers like TensorFlow. They offer a very good power efficiency, and they offer some approach to exploring the design space, but that remains relatively coarse-grained by, for example, supporting just a few quantizations or a few power modes. And finally, we have FPGAs, which are reconfigurable arrays of basic hardware elements like logic elements, memory elements, and which offer really the most flexibility and a really fine-grained approach at exploring the design space. For example, by taking the most advantage of low-bit quantizations, but they require to design a specific hardware architecture, which can be particularly challenging with deep neural networks, especially since we have like strong resource constraints compared to other devices, especially in terms of memory. And so in this thesis, we chose to focus on implementing an FPGA, particularly for this approach that they give at having a fine-grained possibility at exploring the design space. And we will later on in this presentation show how they compare to embedded GPUs. So as I said, deploying deep neural network on FPGA is associated with several challenges, which in the literature are often tackled by exploring and applying model compression techniques like quantization, pruning, or model scaling to reduce the computational and memory footprint of the model. And on the other hand, exploring the design of efficient hardware architectures to accelerate these neural networks, and also often a bit of both. But one aspect that is overlooked in the literature is the contribution to the structure, the design of the neural network itself to the performance of the whole system. Meaning that there's a relationship between the neural network design and the performances, and that this aspect in particular is. Sorry, I think we have an issue with the sharing. Il faut remettre sur. Oui, mais c'est pas moi qui l'a télécommandé. Tu peux essayer. Qu'est-ce qui se passe? C'est une image génique. C'est une question derrière. On lui demandait de répondre. Pas la vidéo, je vais rebrancher déjà. Quelque chose. Ça arrive. Voilà. Ça la vidéo. Non, c'est pour la vidéo, ça ne coupe pas la vidéo. Vas-y, réessaye là pour voir. Juste réessaye. Voilà, justement. Bah, on n'est pas sur le port, j'ai dit.
Tu ne peux pas essayer dans une école des télécoms, hein, sinon.
Olivier. T'as vu ton PC? C'est pas ça marche pas. On sait pas. S'il arrive à la ouais, je vois comme. Je ne connais pas. C'est pas un gros cas. Hein. Bah, le mieux serait de couper la vidéo pour savoir si c'est pas avancé. Non, pas la vidéo. Ouais, mais ça ne marche pas. Tu vois, sinon, PC, ça marche. Sinon, c'est que si tu le mets sur Webex en direct et tu diffuses. Ouais, mais le problème, c'est la couper la vision. Il est en vrai. Du coup, si tu partages, ça va le faire. Oui, c'est pareil. Ok. Ouais. Ah. C'est à la même.
Sorry for this interruption. Is it okay now? Can you see online? Can you see the sharing and the presentation?
Yeah,
Oui.
it's good.
Okay, I'm very sorry. Okay, so let's resume. So start over on this slide. So I was saying that implementing FPGA, implementing deep neural networks for semantic segmentation FPGA is associated with several challenges that in the literature on the field is often tackled by or addressed by exploring model compression to reduce the memory and computational footprint of the design of the model, through methods like quantization, pruning, or model scaling, or designing hardware architectures, and often a bit of both. But one aspect of the problem that is often overlooked in the literature is the contribution to the neural network architecture design itself, meaning that there's a co-design between the deep neural network and the hardware architecture to explore, and that finding an efficient hardware design is a conjunction of all three actors and not just model compression hardware architecture design. And so in this thesis, I've partially focused on this aspect of the problem. So in general, the background question of the thesis is what are the keys to achieve high accuracy, high throughput, and low latency on FPGA with semantic segmentation deep neural networks? And so in this question, we'll come through two claims. The first one is that the contribution of producing new architectures, DNA architectures, to the performances of the network is overlooks one aspect of the problem, that is the training procedure itself, meaning that we can obtain very good performances with appropriate training procedures without having to employ extremely complex networks. And the other one is that exploring hardware-oriented neural network design is extremely important to achieving top performances in all the three metrics. To support these claims, I will present two of my principal contributions. The first one being the implementation of a ResNet 18 UNet deep neural network, which highlights the limitation of unit architectures and the classical approach of just having compression and hardware design. And the second is the study of a hardware-oriented neural network design based on ENet, called PENet. And finally, I will wrap up this presentation with conclusion and perspectives on the subject. So as a first step into implementing deep neural network for semantic segmentation on FPGA, we chose to go with UNet. So UNet is a semantic segmentation network that was invented for medical imaging initially, and that introduced this idea of having an encoder-decoder structure where the encoder and the decoder are the mirror of each other, and we have shortcuts or skill connections between elements of the encoder and the decoder that help the network retain global information while training. And so it's been published in 2015, but to this day, it's still a very standard and very widely used network structure in a wide collection of domains. And so this therefore constitutes a very good baseline for implementation. So we built a UNet based on the encoder of a ResNet 18 network, which is also a golden standard classification network, by removing the classifier part that's at the end of the network, and then plugging the UNet decoder. So this gives this overall structure of the network where we end up with something that has 14.3 million parameters, and we have on the left in blue the encoder blocks that are from the ResNet 18 network, and on the right in green the blocks of the UNet, and importantly the skip connections between some blocks on the encoder and the decoder. So we wanted to implement this network on AMD RVU250 FPGA, and since designing a hardware architecture from scratch would have been very time consuming and was not the goal of the thesis, we looked into frameworks that helped generate FPGA architectures for deep neural networks. And so these frameworks can be roughly separated into two categories based on the type of architecture that they generate. The first one being what I call deep learning processing units, or DPUs. Sorry. Which are systolic arrays that are designed to accelerate matrix operations or several nonlinear operations that are found in deep neural networks, and can be used by compiling the model into a set of instructions that are sent to this array. So since we use the same bit of hardware over and over again through the inference, it's very resource efficient, and it has a low development time, and since it's relatively agnostic to the structure of the neural network, or to some extent to the number of parameters, it's compatible with most networks. However, due to several data transfers between the host and the FPGA, it's relatively limited in performance, especially in latency. The second category is pipeline data architectures, which propose to this time deploy the whole network on the FPGA, where each layer has a specialized processing unit, and each of these processing units are connected in a way that mimics the structure of the neural network, and it follows the same data path. So this type of architectures have the advantage of being able to reach very low latency and high throughput, and offer a lot of customization to explore the design space. But they tend to have a higher resource usage than DPUs, and also put more constraints on the neural network design. For the goal of the thesis, we found that DPUs were not very satisfactory in terms of latency. So we chose to go with pipeline data architectures, since we wanted to explore low latency inference. In terms of framework, we chose to go with Fin for several reasons. So Fin is an open source framework from a research team at AMD. And so without going too much into details, the basic ideas of Fin is that we start from a high level definition of the model that's in PyTorch. We can then apply some quantization using a library called Blevec. And once we have this trained and quantized model, we export it to NNX, which is a graph-based representation of the network. And then this graph is processed through several transformations in the Fin compiler to associate each element of this graph, each layer, to a dedicated hardware accelerator, a dedicated processing unit, which can be then customized for several options like parallelization parameters, so on and so forth. And once we have this graph of hardware layers, we can use HLS tools and synthesis tools like Vado to produce this pipeline architecture. And based on the type of FPGA that we use, we also have access to a driver built around the Pink library, which makes it easy to deploy the model on the target and have a very easy to use driver to perform some tests. So going back to the neural network itself, it has a 68% MIU on cityscapes in floating point. And since some quantization is required for the development of the FPGA, both to save hardware resources and also because FPGA are much more efficient with integer operation than with floating point operations, we chose to apply to use quantization over training using uniform integer scale quantization. And then the question was, how many bits should we use for the activation and weights? And so we conducted a small study where we trained the network using different quantizations from 2 to 8 bits. And we found that the better trade-off was to use 4 bits for the weights and activations, except for the first and the last layer, which are kept in int 8. And so this configuration allowed the network to reach 63% with the quantized version, 63% MIU. One other important aspect when deploying a deep neural network with spin or in dataflow architectures in general is that we need to introduce buffers in the forms of FIFOs between the elements of the pipeline to balance the data consumption and production of the different elements and prevent bottlenecks. And in the case where we have a linear simple topology like here, so where we have a very straightforward pipeline without complex structures, having insufficiently sized FIFOs will only lead to a lower throughput. But in our case, where we have a residual topology, like the blocks in the ResNet or in the UNet or the shortcuts between the encoder and the decoder, we have a situation where we have two branches coming out of the application and then being merged back together later on in the network. And in most cases, one branch is going to hold much less computation than the other, and so we'll have much less latency than the other. Therefore, we need to introduce a large enough FIFO so that we can preserve some form of synchronicity where the branches are connected back together. And if these FIFOs are not sufficiently sized, this will create a deadlock situation where the data is completely stalled at some point in the pipeline, and it completely prevents the architecture from producing an output. So this means that shortcuts are not trivial at all with dataflow architectures, and they must be very carefully taken care of. So, for example, in our ResNet 18 network, as a ResNet 18 UNet network, the longest shortcut, which is between the encoder and the decoder, here goes approximately through 60 layers. And to implement it and still have an output, we needed to put a FIFO with the depth of at least 2 to the power 19, is roughly 500,000, which is significantly huge. Nonetheless, we managed to implement the network on LVOU 250. So we use roughly 80% of the VRAM, 30% of the URAM, which is a very large amount of the memory resources of the FPGA, especially considering that the FPGA is very large. So the design reaches 134 megahertz clock. We had to downscale the input resolution to 256 square, mostly to save resources. And based on the depending on the batch size, the the design is able to reach 23 FPS peak throughput and 44 millisecond per input latency. So in summary, these results are really encouraging if I follow pipeline dataflow architectures. Even if we did not really have performance that are sufficient to really be relevant for real-time inference, we can see that we are still in the correct range, in the correct order of magnitude in terms of latency. This also shows that shortcuts between the encoder and decoder, although they are insignificant and trivial on GPU, can lead to many issues on FPGA when working with pipeline dataflow architectures. And it also shows that just having a compression of the model and an efficient hardware architecture design is not enough, that the neural network architecture design must be very correctly studied. And so starting from this observation, this calls for to go towards more efficient architectures. So we did by studying a hardware neural network design based on ENet. So ENet is a encoder-decoder semantic segmentation network published in 2016. But this time the encoder is much longer or much bigger than the decoder. And it's built as a succession of bottleneck blocks, which are inspired from ResNets and follow more or less the same structure as you see on the left. So we start with a pointwise convolution that reduces the depth of the feature map by a certain factor named the projection ratio to reduce the computational complexity of the middle convolution here, which based on the type of bottleneck that we use and based on the position in the network can be dilated or asymmetrical convolution, which are two ways to reduce the complexity of convolutions. It can be a transpose convolutions, which is a form of image upsampling that is used in deep neural network and that is computed as roughly the opposite or the reverse of a convolution. Or it can be a regular straight-edge convolution when we want to apply downsampling. After that, we have another pointwise convolution which projects the feature maps back to a space with more channels. And importantly, we have the skip connection between the output of each bottleneck block. So this gives a very lightweight architecture with only 350,000 parameters. However, if we go back to this diagram, we see that ENet is all the way down here with only 58% MRU on cityscapes, which is rather low performances and make it seem like not so much of a good choice. But the literature has shown that there's a bias in producing, in the way that new models are evaluated, and by claiming that the performances are just due to having a better architecture, whereas it's mostly depending on the training procedure. So it has been beautifully shown in the paper on classification from Whiteman et al. called ResNet Switchback, where they showed that with the ResNet 50, when you apply a better training procedure by changing the training parameters like the running rate, the scheduler, the optimizer, the number of epochs, or applying extensive data augmentation techniques or using different cropping, you could improve the top one performance on the top one accuracy on ImageNet from the original 75% to over 80% and make the ResNet 50 competitive with visual transformers, which were deemed to be superior to the architecture. So inspired by this observation, we chose to take a closer look at the possibilities of ENet and also applied a more training procedure on cityscapes inspired by a paper called RegSeg. So we also increased the number of epoch, changed the training parameters, applied very specific data augmentation techniques, and changed the crop and resize window at training. And using that, we've been able to increase the performances of ENet from the original 58% to 70.5% on cityscapes. And we also conducted a small ablation study showing that each of these changes on the procedure contributes to the increase in performance, but mostly that they are relevant together. We have similar observations on Cambit, where we improve the semantic segmentation performance from 51.3% to 77.6%. And so this shows that in the context of semantic segmentation, training, like the contribution of the training procedure to the performance is greatly overlooked compared to the contribution of having a more complex and modern architecture, which means that we can reach very good performances with simple and lightweight architectures. And if we go back to this diagram, we had ENet that was all the way down here, and just retraining without changing the structure, we bring it up here, which makes ENet look like a much more interesting choice on this Pareto curve and make it exhibit a very good performance to parameters ratio. For the sake of fairness, if we retrain other lightweight encoder-decoder semantic segmentation network using the same procedure, we see a slight increase in MRU for most of them, but this increase is not as important or as as important as for INET, except for ESP-INET, which is another lightweight semantic segmentation network, kind of the same range, but we still prefer INET over ESP-INET, mostly for its much more simple architecture. So we dealt with the low semantic segmentation performances, but we still had to adapt the structure of the network to make it compliant with the implementation on FPGA with Fin, mostly to several elements that are linked to how Fin works in details. So these modifications include replacing the activation function from prelude to regular value, moving the activations before additions, like the element-wise additions, reshaping the transfer solution kernels, and very importantly, in the bottleneck blocks are used in the decoder where we apply upsampling. We changed the method that was used to do the upsampling in the shortcuts from a maximum pooling to a transfer solution. And in the bottleneck blocks are used in the decoder for downsampling. It's something similar by replacing what was used to downsample the image with a maximal concatenation. We replaced it by a pointwise threaded convolution. And so doing so removes the necessity to carry the indices from the encoder, so from the downsampling blocks in the encoder to the upsampling block in the decoder. And as we've seen, removing the necessity to carry information between the encoder and the decoder is extremely relevant. We also need to introduce a value or an activation layer between the two convolutions of the asymmetrical convolution, and simplify the initial block so that that's used at the beginning of the network to perform the first downsampling. And to see the influence of this change to the performance of the network, we trained it with using the same quantization parameters as was represented in UNet, so using 4 bits for the weights and activations, except for the first and last layer, and apply this modification one after the other. And so we see that some of this modification marginally increase the MIU, while some decrease it, especially moving the activation. But overall, we end up with a version that's implementable on FPGA, and so where all these modifications were necessary, and that has less than 1%. There's less than 1% behind the floating point baseline in MIU. But we note a significant increase in the number of parameters and the number of operations required by the network. So this time we implemented this on Zinc Ultrascale plus FPGA, which is a more relevant choice of FPGA for embedded system, and using 512 times 206 input resolution. So the design uses roughly 60% of the loops in the VRAM, but we also didn't use any URAM or DSPs that were available on the FPGA, and reaches a 250 megahertz clock. In terms of performances, we can reach up to 47.1 FPS in a 21 millisecond per input latency, which is not only twice as good as the ResNet 18 UNet, but also constitute performance that are relevant for real-time inference. So nonetheless, we wanted to see if we could further improve the hardware performances by modifying the design, especially since all the modifications that we needed to do previously have increased the complexity of the model in terms of number of parameters and number of operations. So we explored several design options, like increasing the projection ratio, which is this factor that determines by how much we reduce the number of channels in the bottleneck blocks. We also wanted to introduce shortcuts between the encoder and the decoder to explore the trade-off that they introduce, like seeing how much they would improve the MIU versus the additional hardware cost of having them, and if it would be worth it. Also, since the literature in semantic segmentation showed that the contribution of the decoder to the performances of the network is much less important than the contribution of the encoder, we thought of simplifying the decoder by changing the transpose convolution to another upsampling method, the nearest neighbor exploration. So we end up with 6 different versions of the network. And if we look at the performance in MIU compared to like the VRAM usage, for example, we have our baseline here, and then if we introduce shortcuts here, so SC1 is the innermost shortcut, SC2 is the outermost shortcut, and SC is having both of them. So we see that we have in some cases, a marginal increase in MRU, but this increase comes at a much larger increase in number of hardware resources and the number of operations, which makes cuts, as we've expected, not so much of an interesting trade-off. On the other hand, increasing the projection ratio from 4 to 8 decreased the resource usage as expected, but also significantly decreases the MRU, which also makes it not a very interesting trade-off. However, replacing the transpose convolution by nearest neighbor interpolation really paid off, as we've been able to maintain the same MRU, but end up with a version of the model that uses much less hardware resources. And also, if we look at the number of parameters and the number of max, we end up with a network that's in the same range or even less complex, a bit less complex than the original INET, so the one that was published in 2016 before applications. So this better version of INET, we called it PINET, and that's the one we get for implementation later on. And we slightly improved the performance of the quantized network by fine-tuning on additional 200 epochs with different scheduler, which brings the MRU to 70.3%, which is only 0.2% behind the floating-point baseline. So we implemented this network into two different designs called PNet-S and PNet-M. The difference between both being the parallelization parameters that we chose for the different processing units. And so in the M version, we increased the parallelization to reach a better throughput and lower latency at the cost of using a bit more hardware resources. And so the design is able to reach a 300 megahertz clock. And in the case of the M design, we reach a 226 FPGA throughput with a 4.4 millisecond latency. So this shows how important it is to explore hardware-oriented neural network design to reach good performances in MRU, throughput, and latency. And so compared to the state of the art of previous implementations of deep neural networks trained on cityscapes, we have a better MRU than previous implementations by at least 5%. In terms of latency, with our M design, we show better latency than previous implementations, except for the INET HQ, which is also an implementation of INET, but applied a lot of compression to reduce to reach very low latency, but at the cost of a significantly lower MRU, which means that we have a better trade-off between hardware performances and segmentation performances. In terms of FPS, our M design outperforms previous implementation, while the S design is kind of the same range of the two best. In terms of resources, we can see that we use generally more resources than previous implementations, especially in terms of loops. But we also didn't use any of the DSPs, which kind of balances out and make it so we are kind of in the same, we are comparable in terms of other resources used. And for also the sake of comparison, we produced a version that's trained on CAMVID. And this version outperforms previous implementations in all three metrics of MRU, latency, and FPS at the cost of a generally higher resource usage. So it's rather difficult to compare really one-on-one different implementations on FPGA because there's so many elements involved. But we can still claim that we have state-of-the-art performances on cityscapes and CAMVID datasets. At the beginning of this presentation, I said that embedded GPUs were also an interesting target in terms of hardware device, and that we would compare them. So we did so, and we had available NVIDIA Jetson Xavier and NVIDIA Jetson Orin Nano. It's quite difficult to compare FPGAs and GPUs in a setting that is extremely fair, but we tried to find a setting that seemed relevant. And we put the GPUs in 50 watt power mode and used FP16 quantization. Each time we performed 1,000 inferences on 512 times 206 inputs. and we measured the dynamic power consumption, meaning the power consumption of just the FPGA chip on the FPGA board or just the GPU chip on the GPU boards. So this gives these results. We see that our S design has performances comparable with the Xavier, while the M design has performances comparable with the Orin Nano. In particular, the S design has a lower peak power consumption than all of the two others, all of the two, both GPUs. Excuse me. In terms of power efficiency, our S design is comparable and even slightly better than the Xavier, whereas it really falls behind the power efficiency of the Orin Nano, which can be partially attributed to the fact that the Orin Nano is on a much more advanced FinFET technology than the FPGA that we're using. So all in all, it's rather difficult to say which one between GPUs or FPGA are the best, especially because it can depend on the way that we compare them and which one of the two devices is the most appropriate is going to widely depend on the use case. So this brings me to my conclusion and perspectives on the subject. In summary, so we showed that applying proper training routines were extremely important to reach good semantic segmentation performances, and that this contribution to the performances was overlooked compared to producing more complex architectures, meaning that we can reach very good performances with simple and lightweight neural network architecture by applying good training procedures. We also showed that studying hardware-oriented neural network design is crucial to reach good performances in really good hardware performances. We set state-of-the-art performances on urban scene semantic segmentation on FPGA, and we showed that we were competitive with the performances of embedded GPUs. So this work has led to several impacts, and first of all, even if the methodology that we studied and presented was evaluated on semantic segmentation, it can be extended to other applications. So this has been shown through a collaboration on the Lizard project on object detection in drones, through a collaboration with the Archantech company on embedded radio signal processing with GPU networks in rocket launchers where they have like a sub 1 millisecond latency constraints, and through a collaboration with AMD on the hardware-software co-design of upsampling methods for super resolution networks on FPGA, and this collaboration in particular is described in the manuscript. Another contribution that is thoroughly described in the manuscript is the several contributions that made to the FIN framework, in which are new transformations and support of operators to help designers implement semantic segmentation network with FIN, and that are published in open source and available on their GitHub platform or the GitHub repository. And so some of these contributions were made as part of a 6-month research internship at AMD Dublin in the team that develops develops FIN. Sorry. And lastly, all the code that were used to generate these architectures and the methodology were made open source on GitHub to help to encourage further research in the field. This thesis also led to several peer-reviewed publications, both in national and international conferences, and also several scientific communications. Mainly, more importantly, three contributions to a tutorial at the APL conference on FIN, where I've been able to present my contributions to the framework for semantic segmentation. And this thesis also leads to open several perspectives in the field. One particularly important aspect is that how in general, in the process of implementing a semantic segmentation network in embedded hardware, we need to reduce the input resolutions to save resources. But this something that's not very much discussed in the literature is that this reduction comes at the cost of a lower MRU in some cases. And it would be interesting to to do some research in that direction. So one aspect could be to use tiling, so only segment one tile of the input image at the cost of a lower throughput, or to study how changing the cropping in the resize window at training and influences the performance of the network on inferring on low resolution inputs. And so this type of work has been done and showed on classification network through a paper called FixRes. Also, another interesting aspect to take also in inspiration from works in classification would be to take inspiration from a paper called FPGA, which showed that we could transform residual topologies that were trained with networks that were trained with residual topologies into VGG-like topologies, so very straightforward linear architecture without using any classification performances, but doing so increases significantly the throughput that we can reach. And as we've seen, shortcuts, even local shortcuts, can be difficult to deal with pipe and dataflow architecture, so that would be extremely beneficial. Another aspect is to go a bit further with the design space exploration. One thing that we wanted to explore was the trade-off introduced by using group convolution with different group sizes. So we did some training with that, but we couldn't go very forward because group convolutions are not completely supported by Fin. So this also calls for more contribution to the framework. And finally, it could be interesting to find a more automatized and wide approach to exploring the design space through hardware-oriented neural architecture such techniques. So this concludes my presentation. Thank you for your attention, and I'll be pleased to answer your questions.
Yes, thank you very much.
So now we will go through the questions of the members of the jury. We will start by the reviewers, and I will give the floor to Andrea Pina for the first set of questions. Andrea?
Okay. Thank you very much, Hugo, for your presentation. Really intensive, but clear, and I appreciate it. So I have some questions. The first one is about when you try just to understand from the dataset, you cite the two different dataset with one with 11 classes, the other one with 19. How many classes are shared between the two? You know, just to understand if in the 19 classes of cityscapes.
Yeah, I think in the 19 classes of cityscapes you find the same 11 classes of Camvid plus additional ones. Like I think Camvid doesn't have things like traffic signs, for example, or I think like for example in Camvid you have like the tramways that I think you don't have in cityscapes. You have the tramways you don't have in Camvid.
Okay.
So yeah, those are examples of additional classes.
So this question is why, or if you have do that but you don't present the result, try to test your network or retrain or fine tuning, sharing the dataset. So using the dataset of Cityscape with to test what you test on Camvid. Say you have two different kind of optimization. One from Camvid, so you are very vertical from database that you try to find the good architecture from hardware, but you test always in separate way. But did you have think you could have a more result if you make a cross correlation between the dataset to test and improve one model?
So I haven't really explored this. So if I understand what it's like,
but what do you think could we? You don't explore it, but do you think that this can improve your optimization, your result, or not?
Well, what I know is that often when papers are trained as deep neural network or semantic segmentation in these data sets, since Cityscapes is larger and also contains the same classes as Camvid, they train on Cityscapes and then use the pre-trained weights to fine-tune on Camvid. And so that's a very standard way of kind of if you can do the more difficult, you can do the simplest use case. But in our case with Inet, we found that, so in particular with Inet, we found that that didn't really work well. We had lower performances when trying to do that. So instead, we retrained from scratch on Camvid directly. But so maybe it's something related to this network in particular, but this is very common to use the weights of cityscapes to train on Gambit. But we didn't evaluate, we didn't evaluate directly without fine-tuning just using the weight of cityscapes on Gambit. But in our case, it wouldn't have led to very good performances, but I think in general that's something that may be done. Yeah.
Okay, thank you. Another question is when you talk about you introduce the quantization in slide 19, if I remember.
Yeah. Sorry, there's a bit of delay between.
No problem. Take your time.
Yeah.
So you finally find 4-bit for weights and activation and int8, and after you give. So this you motivate this. You take this result because you have the 62% of MEU, but this depends on the classes. The MEUs depend on. So the question is, if tomorrow I add one classes or we change the classes, how this first step for optimize and find a good hardware implementation could be impacted. I needed to refine and find the new quantization, or there is a trade-off that no, I think that I can add or change one classes and this quantization could stay fixed.
I don't know if quantization adds a layer to the problem. I think generally it falls in the problem, the question in deep learning in general of incremental learning, or when if one class of your data set, how can you retrain or fine-tune your network so you can adapt to this? I don't know if there's any relationship with the quantization. The choice of quantization was here not just generally based on the MRU itself, but also in how much hardware resources it led when implementing it, and based on the target that we used. So to answer your question,
my question is, this question is because I don't understand what you want to say or the meaning on quantization aware training.
Oh, okay.
If you are aware training, why you justify your result of quantization with MEU?
Okay, no, so quantization aware training is the idea that we find when we apply the scale quantization, so we quantize by multiplying by scaling factor, and so we train the network to find the scaling factor during training the network to find the appropriate way to shift from floating point representation to integer representation. But then, just like the weights are. The value of the weights are depending on the class and the data sets and everything. I assume that the value of the scaling factor is probably going to have to change if you introduce other classes or more data in general. But the justification of the good or the good trade-off is based on the MRU performances, but also the balance of how much MRU we have and how much resources we use.
Another question is about when you talk, when you start to present ENet, all the ENet work that you have done. The first question is, okay, you start with ENet as a baseline. You try to understand how you can, is a small model, we can do more better with this model if we retrain or we do something more. But after you propose some modification, some update of the ENet model, and we say, okay, I test. I think it's in the slide 29 or 30 at the end when you compare all the modification of the update.
It's very sorry. There's a lot of delay
29 or 30. Okay, 30.
This
I
one?
think
Yeah.
no, it's just after.
After?
After.
No, here's what I speak about 5,000 shortcuts.
Yeah, when you make the okay. So in your manuscript is is when you talk about the model adaptation of the init with the activation replacement, the transposed convolution, reshaping, and.
Oh no, yeah, no, you're right. It's here. Sorry. Yeah, okay.
Okay, you say after you present a table with all the performances, and you say I do it in the incrementally way.
Yeah.
Incrementally, meaning what? That you test one, and after you test another one separately.
No, not separately.
Okay.
Increasingly, so it's.
So
first we do
this is
one,
the sequence and say you add each time.
Yeah.
Okay.
It's incremental, so it's not like a ablation study where we only change one thing. It's we add one after the other, and what the order is completely arbitrary.
Okay. It's more clear. Because if you do separately, I don't understand.
Okay. Sorry for the confusion.
And after the last part of question that I think it's for me it's very how I write in the report. The last part that you compare the result of the power consumption.
Yeah.
The first question is how you have done the measurement of the power consumption of the FPGA board. Because what is missing in your presentation that you need to take into account that your boards are not totally FPGA. You are in a system on chip, and you have a processor part, a lot of stuff inside of the circuit, and after it's very difficult to make a really measurement power on this kind of board. So the first question, how you make this measurement? And the other side, you don't mention how your final design, how is partitioned in the SoC. You use or not the processor for do something or not? No. Okay.
It's just so the processor is only used with the Java to send and retrieve data.
Okay.
And then
for the interface.
Yeah, it's just the interface.
Okay, but so your measure how you measure your on the card on the board ZU19 the power.
Yeah, so since it's on these boards or in merge FPGA boards, we don't have access to exactly the power of the FPGA. I measured like the static power consumption, and then ran the inferences and measured the dynamic power consumption, the power consumption, and then subtracted the static power consumption.
But the measurement of the power is where on the board?
It's it's at so there is like a
in the XIDC pinout. There is a converter that. It's on the power supply.
It's on the power supply, I think.
Yeah, but the power supply is the power supply for all the board.
Yeah.
Yeah, so you take into account that in the SoC there is some different paper that show that the most power consuming part is the processor.
Yeah,
without you don't use the processor. In this, I think that the FPGA is less power than this if you take into account only the FPGA. But the problem is how separate the power consumption. So your comparison is not really fair for the FPGA.
Okay. Yeah, but it's difficult to find a really good power consumption of just the FPGA when you only have access to one value. So that's why I thought it was. Well, maybe. So I thought that when since we don't use the CPU so much, but really just to send data. If we compare if we measure the whole power consumption of the board during the inference on FPGA, during the neural network inference as on an FPGA, most of the difference in power can be attributed to the FPGA. But I agree that it's not very precise and accurate measurements. But I think that's kind of the best I could do with what was available. But definitely.
And last question, just in these slides, perfect. I try to understand when we make the comparison with GPU, why not? But what you have implemented in Jetson or in EGX is not clear which PNet you the same one.
Yeah, the one where exactly the same network that the one we implemented on FPGA.
Okay. Which one? PNet S or M?
Oh no, well it's the same, because the difference between the two only are relevant for the FPGA implementation, because the difference between both is just the parallelism parameter that we chose for the processing units in the pipeline architecture. but it's the same network. So the difference between the two implementations are relevant, makes sense on the FPGA, but it's basically the same network. And it's just how much resources and where did we want it to land on the trade-off between hardware performances and resource usage. But it's for the FPGA.
Okay. And the very last question, because you presented at the beginning the application, the use case. So after all this work, which architecture you think is better for the car?
For the car?
Well, at the end, what if you need to integrate something at today? But perhaps tomorrow we can do better. But
it depends on the architecture. It depends on the device basically that you want to use. But assuming that you want to use FPGA with pipeline data for architectures, I think something like Inet is perfectly fine. It is very lightweight, so the power constraint is going to remain very low. But if I wanted to have something even more efficient, we would need to have a less complex structure with very straightforward linear topology. I think if we could have good performances with this type of architectures, it would be very good for FPGA. But in general, it really depends on the device that you're using. If you're using something like an embedded GPU or even a systolic array on FPGA, you don't care so much about the structure of the network. And then the only question is what trade-off can you find between some form of quantization, so the performances, and the, I'd say, in the latency or the inference time. So the choice will be much more simpler with systolic arrays or embedded GPUs than with pipeline data for architecture. I don't know if that's answered the question or if I made it.
Yeah, the question is because I see in the first slide that you mentioned 30 frame per second and 10 milliseconds for latency.
Yeah.
And depends on this, I think, on the speed of the car.
Yeah.
And so
yeah,
I don't know what are the upper and lower limits in terms of performances if you needed to apply this kind of models. This is just a question for in my mind that when we are ready to go to put inside this into the car. And the other part of the question is if you have the time and you are free to do what you want, which kind of FPGA architecture, how you imagine to change, where you need to change the FPGA architecture that mostly the last 20 years is always the same, where more fine-grained or what else, DSP, okay, but the block, the base is always the same. If we can change, we need a different memory computing architecture that are more adapted for this kind of implementation, for that take into account the quantization, take into account the optimization.
That's a good, it's an interesting question. So just the first part of the question was, I think, on the latency kind of boundaries. Just so I said 10 milliseconds. It depends from system to system, and also depends on the use case. Like, is it going to be embedded on cars that are gonna like drive in urban in cities where you only go as far as 50 kilometer per hour technically, or is it going to be on the highway? And so like, I think with the estimation that we made is that if you drive at 50 kilometers per hour and you're like 1 meter away from an obstacle, you have approximately 70 milliseconds to take a decision. So that gives this kind of order of magnitude. So if you go higher, if you go faster, it's going to be lower. But it's difficult to give an exactly precise value. And then on the FPGA architectures themselves, I guess it would depend what is, if latency is really important, what is bounding the performances of the design. Is it memory bound? Is it computationally bound? Is it the IOs of the FPGA itself that are slowing it down? So I guess it also depends on which context you implement the FPGA. I think if you want to go very fast, you would generally like to not have a system on chip with a CPU and have the sensors or the cameras being directly connected to really take take advantage of the FPGA. So if your system is memory bound, even though like the internal memories of the FPGA are already quite fast, maybe something going to like in-memory computing or something could be interesting if you really want to reach extremely low latency. But with already standard FPGA architectures, we have like in the order of a millisecond of latency. So I don't know if it would make a lot of sense to try to go even lower than that for autonomous driving. For other applications, maybe, but for autonomous driving. So I don't really, I'm not quite sure what the best answer would be. I guess it's going to. So the change that would be interesting in the FPGA architectures would depend on what is really limiting the throughput or the latency of your implementation. And in my case, I'm not quite sure.
Thank you very much. Thank you.
Thank you, Andrea. So the next reviewer is Olivier Santiez. So Olivier, you're on stage.
Yeah, thanks a lot. Can you hear me well?
Yes.
Okay. So thanks a lot, Hugo, for the very clear presentation. I was very happy to read your thesis. Sorry for not being in Brest. Finally, I'm the one who is maybe the closest to Brest, but I couldn't make it. I had some courses this afternoon. Well, but anyway, sorry for that. I would like first to highlight your contributions because they are really interesting and novel. And I also would like to particularly highlight the fact that you did a lot of. That's what I understood from reading your manuscript. You did also a lot of contribution to the Fin framework, especially. So this also requires a lot of time and. Yeah, that's also something that we should account for your thesis. So then I have some questions. The first one is maybe I will start from technical to more high. So did you consider other arithmetic and number representation, like for instance the mini floats? Sorry, Anastasia, I have to ask this question. Is it something that you considered, or did you right away start with integer?
Oh, you mean like?
Yeah, I mean 8-bit floating point or below even.
Below, you mean like still integer but like binary or ternary or?
No, I mean floating point.
Floating point. Oh, no, not really. I think we assumed that we had to do integers in general with FPGAs. It's not just an assumption. It's clear in the performances in terms of energy consumption and speed that FPGA are more efficient with integer representations. And also we didn't go very far with the quantization. There was not really the main focus of interest of the thesis. So we saw quantization has really a tool to compress the model and trying to find an appropriate trade-off, but didn't really try to go into things that were extremely particularly innovative in the way to use quantization. So in short answers, no, not really.
Okay. So why am I asking this? So we have a paper, I think, two years ago or something about mini floats for segmentation. I don't ask you to have a look. If you're interested, you can search for it. But the good thing with very small floating point, especially because you are using only lookup tables and you don't really use DSPs as far as I understand. And when you go for very small floating point, the hardware cost is finally even smaller than for integer. Could be even smaller.
Okay.
But okay, if you didn't look at it, that's not an issue. The second question is about your quantization. So I understand that you didn't put some effort on the quantization. So it's slide 19, as far as I remember. So Andrea already asked. So I understand that I was not sure if you really used quantization over training. So it seems to be the case. So simple question could be so I assume that you use the QAT techniques provided by Fin. I can't remember the other framework that is doing the QAT.
Brevitas.
Yeah, exactly, Brevitas. But did you also compare with post-training quantization or post-training quantization with kind of fine-tuning? Did you have the curiosity of comparing both approach on your application use case?
No, not really. I mean, I know that. So, in general, what I found in the literature is that, especially for low bit quantizations, like 4 bits and below, quantization retraining gives much better results than post-training quantization. And so I kind of took the choice of just looking into quantization over training and still try to kind of optimize this and choose the correct quantization. But in a way, you could see that the fine tuning that we did on Inet at the end was kind of post-training quantization. Well, we didn't change the quantization, but we did some fine tuning after the quantization over training. So it's a bit far-fetched, but you could say that it's kind of a mix of both approaches. So no, I did not really try to apply post-training quantization, mostly because I saw that it was often not as often in many cases didn't give as good results as quantization or training for low bit quantizations. But
okay,
I agree that could have been an interesting thing to do, and maybe it would have led to different results.
Okay, thanks a lot. So then it's about the choice of architecture style. So of course you are linked to Fin, so you have some constraint on that. But it's sometimes good to justify the choice. So you choose the pipeline dataflow structure, let's say. So the Fin approach, let's say. I will not ask if you compare with other architecture style, but at least what is your? Can you motivate this choice? I would say compared to what we can call layer by layer or sequential. Or using more, something like a systolic array or whatever. How can you motivate this choice?
Yes. So just as precision, I tried to use other style of other architectures. At the beginning of the thesis, I tried to use Vitis AI to use like a DPU, but it did not really lead to something very interesting. It was rather difficult to use the tool itself and outside of the already available use case and networks that were implemented. And well, so I tried a little bit to go to see what we could do with DPUs, but if you look at so the second part of the question, I can motivate this choice. In general, if you look at different implementations of networks in the between like GPU style architectures or systolic array style architectures and pipeline dataflow architectures, you find that for the same structure, the pipeline dataflow architectures are generally faster. When I looked at the previous implementations, one example I took was the ResNet 50 implemented with Fin, and same ResNet 50 implemented with Vitis AI, and the difference in throughput and latency was extremely large. And if we come back to this table, for example, if you look at the latency, So it's not always reported by the papers, but if you look at DPU's implementation, so namely, maybe I can, so like the DeepLab v3 or the ANET on DPU, and the order of magnitude of latency is like 100 times higher than with pipeline data flow architectures, even in previous implementations. So I think this type of result really show that pipeline data flow architectures are much more interesting to reach low latency inference. So that's really mainly what motivated my choice. It really became clear that it would be extremely difficult to have an implementation on this type of systolic array architectures with less than 10 millisecond latency.
Yeah, I'm a bit surprised that you have so much of a difference in latency between the two architecture styles. But okay, but let's see. It depends how you made it. So at one slide, I have seen some results on an Alveo board, and it was quite because the drawback of pipeline data flow architecture, you usually require a lot of memory, and all the model has to fit inside. It has also clear limitations, but you improve them. And but you have some results on an Alveo, and for me it doesn't sound very embedded. So, and it was already almost full, but maybe it's on the first part of your. Maybe it's not that important. Yeah, it was this one maybe.
Yeah, sorry.
The one where you show that the residual connection are not good for your FPGA.
Yeah, so you're absolutely right. LVO are not embedded FPGA or embeddable FPGA at all. But like the reason why we used it is because we really just wanted to have first implementation and see what were the limitations, how difficult it would be to implement on FPGA. So we took and we, even with the LVO U250, in the first experimentations, I had issues implementing the design with the amount of memory that was available. And so we kept with LVO U250 because it's such a large FPGA that it was easier to find a way to implement it. But the end goal was not to have something embeddable. In the end, we don't even have performances that are really good for real time. So so it was like a choice of really just context, and the goal was not to go towards something embeddable. That's also the reason why we changed the network from ResNet 18 UNet to ENet. So all the reasons linked to the shortcuts are presented, but also it became clear that it would be difficult to have good performances on the FPGA that is more in the range of something that could be embedded in a car.
Okay, no, but it's clear. It's before you move to some optimization. So you mentioned that so you do a lot of stuff to optimize, and you mentioned that in your perspective. But I was curious about using neural architecture search for trying to automatize finally, because you did a lot of work on manually optimizing the thing. So, well, its perspective. So, but what is your opinion on that? Do you think that you can try to automatize your transformation with these kind of techniques?
Okay, so thank you for the question. I will come back to the part about transformations, but I don't know the Adonis literature a lot, but I've looked a bit into it because I thought it was interesting. And what I found is that in general, papers use standard NAS approach, but include other metrics than just the performances of the network as a way to find the good architecture. And they try to evaluate the hardware performances by introducing a computation of the latency. So sometimes it's directly measured on the device, like there's a paper, MNASnet, they directly measured the latency on mobile phones of the network each time they search for each time they evaluate the architecture during the search. And you have other papers that do an estimation of the latency. And usually this estimation is based on a lookup table. So they have a table where for each operator they have how much latency this operator takes on the device. And then the total latency is just the sum of all these operators. So in the case of my work and using Fin to have an estimation of the latency, for example, just in the case of FPGA. So the first approach of directly measuring on the device, I think, is completely out of scope. It takes a very long time to implement the design on FPGA, and also coming back to your question about the transformations, it's difficult to have so like the transformation are really I would say kind of ad hoc approach that you try to find the correct transformation for the structure of the network that you're using, so it can be mapped to hardware layers. But it's difficult to find a set of transformation that would work with all network structures, which means that in all the experiments that I did where I show BRAM and LUTs estimations and usage, etc. Every time I had to adapt the transformation or the order of transformation that are used manually to reach these steps. So it's difficult to automatize this process. It depends how large your search space is, but it would be difficult to optimize all the process of compiling the different network architectures with Fin in a time that would be relevant for NAS. And the second approach, I think, it would be interesting to have an estimation of the latency without having to actually implement it or even go to some steps of Fin. I'm just wondering, I think the approach of just having the sum of the latency of each of the operator wouldn't be accurate enough, as I've showed with ResNet 18 UNet. For example, things like shortcuts are extremely deadly to the overall latency. And so you can have a very good latency by computing the sum of the operators, but then when you try to implement it, due to shortcuts and the fact that you have to introduce large memories, you cannot reach this same latency. So we would need a way to estimate the latency cost of having different elements in the structure of the network, like the shortcuts, for example. And so I'm not quite sure how to proceed. So I think it would be extremely interesting and very valuable to have NAS approach and to automatize the search of appropriate hardware architectures. But we would need to have a good way of estimating the latency of the different network architectures. And for now, I don't see a very straightforward solution to that issue.
Okay, thanks. So you say it's difficult, so that's where it comes interesting. I agree that
I would say
to have a hardware NAS for pipeline dataflow architecture style would be maybe one interesting research in the future.
I agree.
Can I have one or two more questions, or is it?
Yes, please.
Okay. So they will be short. So I'm not an expert in semantic segmentation, even if we did some work. But it seems to me that the latest models, the state-of-the-art models, are fully convolutional network, or also maybe certainly vision transformers. I think that you have deep lab. I think it's in your results. So. Can you comment on that? Because it solves a lot of, you don't have residual connection, so could be. In your case, having fully convolutional network could be something.
So I don't know any
I don't think there's any performing network in the state of the art that are absolutely just fully convolutional network. I mean, like really straightforward, just CNN. Even deep lab, so it's just convolutions, but there's deep lab has also this idea of splitting the network into multiple branches that are going to be able to see different field of views during training and then merge back together. So they have a different, there is a different structure than the encoder decoder that I've used. That is kind of a multi-branch network, but I think it will lead to the same kind of issues that you have, and that in general with pipeline data for architectures, or even with Fin linked to all the transformation works, it's difficult to process networks that have a lot of structures with like multi-branch and things like that, or to use something that's very widely used in also real-time semantic segmentation network is like current pooling, which is something where you have a lot of branches that are then connected together differently, and this type of structure is very used, but it's difficult to implement with Fin or with pipeline data for architectures in general. And coming back to the first part of the question, so like the state-of-the-art models are on the top right corner here are still based on visual transformers, and even some are extremely large, like Interlimit, which is like really a foundation model, and but like so some of them are still use some high-end or state-of-the-art models still use convolutions, but really the best performing one now have visual transformers.
Okay, thank you. And my very last question is finally is the same as as Andrea's very last question. But so I like FPGAs, huh? Don't get FPGAs. This is my favorite playground and stuff like that. I like Fin. I like it. But finally, for your autonomous driving, would you go for GPUs or for FPGA? Based on what all the effort you put during 3 years, I would go for GPUs based on your results. That's what I want.
No,
based on your results, in the end, I would say, okay, well, let's go for the.
Okay, so it's based on the results, and it's a fair point. I think GPUs are much easier to use in general, and they have like very good performances, except like especially the Nano. I still think there is some place for FPGAs in specific use case for semantic segmentation. For other applications, it's often more clear, but for semantic segmentation, especially because, well, it's not necessarily very highlighted in my results, but you have with this type of architectures, you have a really wide range of design points that you can find, and like I try to have like the best performances, but we could say if we don't need more than 30 FPS, you can reduce the parallelization parameters, use something more simpler. You have your 30 FPS throughput, and then you have a much lighter architecture that is going to consume even less power than what I have already, and this trade-off is not really offered by GPUs. So GPU have different power modes that you can choose, but in general I found with measures that the power efficiency remains the same. So like when you reduce the power, you reduce the throughput of your of the GPU, and then it's really relatively stable. I think there's a table about that. No, sorry, there's not. I'm confusing with something else. So with very low, when you have very low power constraints, I think it can be interesting. Also, it depends on how your GPU is implemented in your system in general. I think with the FPGA, it's much easier to think about a system where you would have, as I said before, like the sensors and the cameras, or the cameras directly connected to the FPGA without having to go through a processor, which or something that would give instructions, which is something that I think you would need with GPUs, or well, I mean, maybe there's cases when you don't actually need a system on chips, but these cases are not really available with the GPUs that are on the market. As far as I know.
Okay, fine. So you're like me, you love FPGAs. I mean, that's the kind of answer.
I agree with your statement. Yeah, no, I agree with your statement, but I think there's still very specific use cases where when you want to go to extremely low power consumptions, FPGA offer you this opportunity. Also, you can take an FPGA and do like binary quantization and really take the full or ternary quantization and take full advantage of it and have something that's has a very low power consumption, whereas that's something that's not available on GPUs, for example. So in my result, it's not necessarily highlighted because I didn't try to go specifically into very low power or very low throughput or low resource usage, I would say, sorry. So in general, GPUs are much easier, and if an industrial asks me what is the most straightforward way to have semantic segmentation in my car, I would probably advise them to use embedded GPUs. But I still think there's a place for FPGA. It depends on the context, as I said.
I do agree. Okay. Thanks again, Hugo. Congratulations for your research and also for your development effort.
Thank you.
Frédéric, you are
Thanks, Olivier. So now we will go through the question of the examiners. So we leave the floor to Anastasia.
Thank you, Frédéric, and thank you, Hugo. Not thank you, Olivier, who had a lot of similar questions than I did on the arithmetic side. So thanks for the presentation, and yeah, it's a very interesting work and very interesting, and you know, on the top approach in terms of the autonomous driving and implementation of neural networks. So the approach of the hardware-oriented and hardware-aware implementation is great, but as far as I see with your research, is that it's very, you know, fine-tuned and hand-tuned kind of approach. What are the generalizations that you learn? Okay, you already said that NAS is maybe a next step, and it's difficult to put in place, and you know, to have again a good methodology for NAS in your case. But what are the dependencies and some rule of thumbs that you learn? Is it something that you can still automate? Is some kind of pre-processing? What are the general rules, for example, for the sizes of FIFOs in terms of the architecture that you use? Have you tried during your process of development to automate these things and to draw the Pareto fronts in terms of the resource usage or even the latency estimation, even if it's a coarse grain?
Okay, so if I understood well your question, you're asking if there's any rule of thumb or optimization of finding the correct resource usage or the correct or an appropriate size for the FIFO. Is that right?
Yes, for example.
Yeah. Okay, so there's some optimization that is already part of FIN. So you have in FIN you have steps where you can find based on the parameters that you give, like the throughput or the FPGA that you're using and the clock that you're targeting. You can find the good parallelization parameters to match these constraints. It works in some cases, but sometimes leads to incorrect results. So there's a mix of manual and automated. And I think to choose the correct parallelization parameters, a general rule would be to try to have a pipeline that's the most balanced possible, which means that where your latency, the latency of each element of the pipeline is roughly the same throughout your architecture. So it's difficult to find the most optimal manually to find the most optimal configurations, especially because something that may not have been clear during the presentation, but that eNet is very, very deep network. I think in the end we end up with something like slightly over 90 convolutions, and so and even more other types of hardware blocks and layers. And so if you want to go manually, try to find the correct parallelization parameters, so all of the parallelization of the input and the outputs of your different blocks match, it becomes very, very difficult. So there's some part of optimization in FIN that are not completely optimal. And same comments on the FIFOs. there's ways to compute the appropriate size of FIFOs, or it's mostly through simulation to find the correct size of FIFOs for, in the architecture that's part of FIN. But it also leads for several reasons, it leads to, especially with residual topologies, and when you have complex structures, it often leads to incorrect results where either the throughput is not maintained with this configuration of FIFO, or it's maintained but it's not implementable on the target, like it uses much more resources, or even in many cases I had the FIFOs that were too large and not necessarily that need to be this large, and I resized them manually, and I don't really have any raw sums to try to find the correct size. It was mostly arbitrary and just well, I'm going to resize all these FIFOs. I'm going to try to test if I can implement it, and then if it runs correctly on the target, and if I have the correct throughput, and if not, I'll go back to the previous steps and start again. So there's some to answer your question more shortly. There's some optimization parts that are already part of FIN, but for now it requires a lot of. In my case, at least, it required a lot of manual changes that were kind of a ad hoc approach of just try and error. But I know that they are looking into more ways to have to optimize these steps and leads to better results, both in the FIFO sizing and the parallelization parameters that are found by the tool to match the constraints that you're giving the system.
That's the thing when you talk about the models and the fine tuning, and sometimes understanding why the model that you implement is does not meet your criteria. Is it because you don't have enough space, or you haven't trained it well enough, or you could quantize more? And I see that you moved from ResNet with 14 million parameters to eNets with 350K. So is there something in between that has more accuracy and that could be implementable under your constraints, but maybe moving some other parameters that you haven't moved?
Okay, yeah, that's an interesting question. Just going to switch slide. I'm thinking about it, but I think so. So also one of the I just want to go back here. Okay. So if you look at this trade-off curve, then see eNet is kind of an interesting choice. So there's other models that have a bit more parameters, but also slightly more parameters, but better MIU. In most cases, the structure, like the complexity of the structure of this network is much higher than with eNet. They have like very fancy and complex approaches that are very interesting, but also made them much more difficult to implement on FPGA. And so we found that after retraining, eNet had an excellent place in this Pareto curve and an excellent trade-off between parameters and MIU. So that's why we thought it was a good idea. And also, second part kind of your question. So even you could say that you want to apply a different type of compression or more quantization or pruning and so on and so forth from one of the models that has initially a better MIU. So what you're going to do basically is you're going to slide it down on this curve. So to some extent you can compress the model and keep the same MIU, but if you want to bring it on the same complexity as eNet or something similar, you're gonna have to I feel that you're gonna slide down on this Pareto curve and end up with something that may be more compressed and as complex as eNet, but will in the end, in the final architecture that you have, will be comparable with eNet. So there's always in compression this trade-off between should I take an efficient or a very high-performing architecture and apply a lot of compression to reduce its complexity? Or maybe is it more interesting to start from a low-complexity network that has that will have the same performances as the most complex but more compressed network? Right. So I don't know if that's answering your question or if there was more to it.
No, that's right, and that's the interesting question to see how do you explore this huge design space. I had a question about your flow. So you're using Gravitas library to do the quantization. Is it easy to replace it by something else that is doing hardware-aware quantization? And in your implementation, can you replace your processing elements and your matrix multiplications and accumulations by something highly optimized and customized, for some particular formats?
So yes, so there's two parts. So because the Brevitas and Fin are two separate things. I mean, they communicate well between each other. They are meant to work well with each other, but they are very two separate things. And so you can replace Brevitas by something else to quantize your model. You just need to have a way to export your model into a quantizer or an NX graph. So a specific format so that Fin can take over, and can use this input. You don't need to use Brevitas. There's other ways in the QNX project, which is a other separate project, but also from the same team, but which proposed this quantizer version of the NX format, and that is needed. And this QNX format is the one that's used by Fin, but they propose other ways than just Brevitas to end up with something that's in SIN format. So you can use other frameworks to train and quantize your model than Brevitas. And then second part of the question regarding replacing elements of Fin, like other hardware blocks, that's definitely something you can use. I think one of the great aspects of Fin is that it's not just a framework, it's really a library, it's a playground where you have a lot of opportunity to really dig into it and change parts. And they propose an implementation of convolutions that's there, but it's really built as you have a library of HLS or RTL components, and then you have transformations to map these components to elements of your network graph. But you can definitely say that, I think I have a better implementation of convolutions. Add your RTL or HLS IP into the library, and then find a way to program your transformation so that you use your IP instead of theirs for the convolution. So you have full hands-on this type of approach. Yes.
That's great. And I'm asking that because looking into some shift and add architectures to replace multiplications and to do some liquid compressions for the accumulators. So this would be interesting, though the development effort is probably something that is consequent.
Yeah.
So I had some other question on the quantization that we're training. So again, about the arithmetic and about the data path sizes. So the procedures that you used, do they use homogeneous weight quantizations? And how fine-grained is the QNX format? Can you also change the accumulator sizes and from also one layer to another?
Yeah.
And have you tried doing this in different ways? And what's your feeling?
So the QNX format and just the support of quantization from Fin in general is extremely fine-grained. You can have arbitrary quantization and use different quantization. I did not go that far, but you can use heterogeneous quantization and different quantization for all the different elements of the layer. So layer by layer, you can choose how much quantization you have, how much bits you have for your activations and your weights. And regarding the accumulator width, it's also something that can be optimized. I did not do it manually because it was not there at the beginning, but meanwhile in the thesis someone proposed an optimized and automatized way to compute the accumulator width based on the quantization parameters and that are given to the layers. So it's no part of the thin framework that you have an optimization of the accumulator width that is fine-grained, so like really layer by layer.
Okay, and I guess I can finish with also a very similar question from previous ones. Will you get into a car with a 70% MIOU for the segmentation task?
Why not?
70. That's a good question. So it's an interesting question because it really raises the question of how important is the MIU of the network to the actual performance of the system when it's embedded, and that's also why it was interesting to try to focus on latency and throughput more than MIU. So I think you have some degree of flexibility of how accurate your segmentation is, and maybe it's better to have a less accurate prediction, but to do it much faster so that you can actually take the decision based on it in the correct time frame. And also there's the idea where when you have a real system with like a continuous flows continuous flow of inputs, so like a stream of inputs, when from one frame to another, between frame to another, the differences are going to be minimal, I would say. So like between one frame to the other, it doesn't change that much. So I think on average, even if you have like 70% MIU on one frame, on each of these frames, you can sort of do an average where the images are not that different from one to another, which is not something that you see in data sets, for example, because the images are randomly shuffled, and so there's no idea of having a sequentiality of image, well, except in the test, I guess. So there's some sequentiality, but not during training, just on the validation. So I guess that's something that maybe can be used. So to answer your question, I would rather go into a car with a 70% MIU, but which can take the decision into 4 milliseconds, than one with like a 90% MIU, but it takes like a second to take the decision.
Great, thank you.
Okay, thank you, Anastasia. And then I will give the floor to Camille.
Can you hear me?
Yes.
Yeah, thank you very much. Thank you, Hugo, for your presentation. Let me also thank your supervisors, Mathieu and Mathieu, for inviting me. And I didn't even come. I'm away too. And it's even if it's always a pleasure to come to Brest, it wasn't possible for me today. But I'm sure we'll have occasion to meet up soon. So thank you for your presentation. Very nice presentation. So you showed your several contributions, including open source software contribution, which is not necessarily the case for most of the PhD defense that we see. So this is noticeable, I think. So you're on a very challenging research topic in the sense that I think in the manuscript you mentioned at some point more than 2,000 on one topic. It's really hard, I guess, to keep the pace following what's coming out, and we know that most of these published contributions are not always necessarily the most relevant. So it's really a challenge to be able to sort out everything and make sure that what you propose is actually not existed in literature and relevant. So for all of this, congratulations. Now, of course, I have several questions. Some of them have been asked already, but I still have some. My first set of questions will be around power consumption. So if you could please go to slides 36 or 37, I'm not sure.
This one or this one?
This one, yeah. Thank you. So in the manuscript, there's no real precise definition of what you mean by, well, there is kind of definition, but my question is, what difference do you make between what you call power efficiency and energy consumption? So in the manuscript, you have two figures, one, this one and another one.
Sorry, I have this additional slide somewhere. Yeah. So that's the same.
Yeah, exactly. Yeah.
Okay. So the difference I would make is is that the power efficiency in FPS per watt gives you how much with a certain power consumption budget. Like let's say I don't want to be over 4 watts in peak power. This is how much FPS you can reach with your system. So like it gives you really an idea of power consumption thresholds in watts, whereas energy efficiency is more how fast are you going to empty your battery. So you have several you have a fixed size battery, and it's like how much inferences are you going to be able to do. And so the relationship between the two is just, it's an integral, right? So like the energy is the integral of the power consumption. So I think they are heavily related, obviously, as we can see in the plot. But to me, they don't represent exactly the same thing and exactly the same constraint. So I think they're interesting to. I think both are interesting to look at.
But if you look at the first one, so frame per second per watt, so you have the number of frame processed divided by some time multiplied by watts. It's actually so number of frame divided by an energy. So it's more equivalent to the reciprocal of an energy than to a power. I don't know if you know what I mean. On the right, of course, it's an energy. But to me, when I saw this, I'm not sure it's really a power efficiency, more like a computation efficiency, which actually is more kind of energy measurements. But okay, I see what you try to show. But I think the power efficiency term may not be the most precise one in this case. Okay, comparison. So of course, just like Olivier, I love FPGAs. And I was also surprised to see that GPUs are that good, well, that power efficient actually. I knew that the latest embedded GPU were quite efficient. You mentioned at the beginning of the manuscript some sort of contests where people had to compete GPUs in FPGA. Yeah, that's the one. And so I think you mentioned half to a third of power consumption, and at the end of your work, basically you kind of end up with around the same ratio. So I wonder. Okay, so let's assume there is no the way of measure power was mentioned earlier. Let's assume it's done correctly and there is no bias in what we see there. My question is, how do we explain that they are so close? An FPGA or dedicated architecture is supposed to be really computation efficient. Every watt and every joule that you spend would be used to bring the computation one step toward the final results more efficiently than usually programmable architectures such as GPU and CPUs. So my question is, according to you, what is this gap? Why is this gap so tight, actually?
Okay, so there's I think it's a multi-layered question, but multi-layered answer. I would say so. The first thing to comment on the differences between the result of this contest and what I showed is that it's not the same GPU, and it makes a very great difference between because the NVIDIA Jetson DX2 that they use in this context is the 16 nanometer FinFET technology, which is the same technology as the FPGA, whereas like the Orin Nano is a 7 nanometer technology. So I think a lot of also the power efficiency of the two devices can be attributed to this technological difference which makes it very difficult to compete with an FPGA when you have such a difference. And then I guess that's also because, well, it's not necessarily, it depends if you compare in terms just of power consumption or in terms of efficiency, like how high the performances can be with an FPGA implementation. I think it also attributed to the fact that it's much more difficult to implement your network on FPGA than it is with GPU, and with GPU you really have a lot of option of freedom to implement whatever network you want, and just have to focus on model compression, basically. Like the architecture of the model is not really relevant, and then it's just how good your compression of the model is, so that you can reach good performances. And also another aspect is I think the compilers that are used by NVIDIA, like the TensorRT compilers, is extremely good. And that, for example, if you compare how fast an inference is on GPU on Jetson with just using like just PyTorch, right? Just use the CPU and PyTorch, and just the GPU, sorry, and just PyTorch, without really any compiling or preprocessing, and using a model compiler with Jetson, I think it's like probably 2 or 3 orders of magnitude. So there's also that the reason is the technology and the software tools which are extremely good on GPU.
Okay. Okay. Now, if we move to the optimization of your network, so you use several techniques. You say at some point that okay, if we have a composition of, let's say, a linear function, we can actually compress this somehow, and you do some sort of swapping too. Extend it in the fin tool. You also mentioned in your work other potential optimization, and for example pruning, and you don't use it at all. So I was wondering why is so. Could you comment on that?
Okay. So there's many reasons. The reason why we didn't want to go with pruning came also a lot from interactions and discussions with the previous PhD student, Hugo. And he worked a lot on pruning on semantic segmentation models, and what he found in general is that there's a huge bias in pruning where papers present extremely good pruning ratios, but they start from an architecture that's very large or that has a lot of parameters. And it comes back to kind of the answer that I gave to Anastasia's question earlier, that you also found that in most cases you could start from a much lightweight and less complex model and have as good performances as taking a complex large model and applying pruning. And so it's also kind of true with other ways of compression, but I think it's particularly the case with pruning, where I'm not saying that pruning is not useful, just that its interest is less straightforward, or is less evident, and it depends from one case to another. And especially with a model like Inet, where we only have 350,000 parameters, I don't think pruning, we didn't try to do it, and I agree that it would have been interesting to look into this direction, just for interest. But with a model with so few parameters, each parameter is important, and then if you try to reduce them, I think it will lead to a significant drop in accuracy. And to support this, you can look at this paper that I talked during when I present this table. So like the third line in Inet HQ. So they based off also of Inet, and they did quantization and a lot of pruning, and so they end up with a very fast architecture, but they have like a 36.8% MRU, which is, well, very, very low compared to the initial performance of the network. So I think pruning would have been interesting. It's just that its interest and its contribution to finding a good performance trade-off was less evident to me than quantization, for example. So we kind of made the choice of ignoring pruning as a way to compress the model.
Okay, I understand. So pruning, if I understand well, is not the way of going because it may degrade your MIO view. But when I see that the amount of memory of your design, we're talking about, I don't know, several megabytes, right, on an FPGA. This is a lot, and well, my feeling is, and what strikes me in your results is that this your implementation and neural network implementations in general is not really about a computation intensive algorithm, but more memory intensive. Well, with very large memory footprints. So I was wondering, out of curiosity, is there work on compressing information, all those megabytes stored in memory, and what are the existing approach?
I I don't know. I haven't really looked into that part of the literature, but probably. I guess it depends which maybe based on different data formats that you're using, you can sort of compress the space that's used in the memory, and also like we use the same quantization for activation and weights, but they don't have the same influence on the resource usage, right? So if you if you reduce the quantization of the activation, you're going to mostly reduce the number of loops that are going to be necessary for the computation, whereas if you reduce the quantization of weights, you reduce mostly the memory that's used to store the rates, right? So it means that we could go with something more heterogeneous where we put more bits on the activation so we kind of preserve the accuracy and because computation resources are not that big of a problem, but we balance it out by decreasing further the quantization of weights so that we use less memory and find a different balance between both resources. So I think that's something that has been done. So having heterogeneous quantization that has been done many times in general. So I would, without knowing too much about the literature on this specific topic, I would say that it would be a good approach to the problem.
Okay. Thank you. Maybe one other aspect on that I had difficulty to understand is about the scheduling of your architecture. So at the first sight, you may think, okay, this is a pipeline with a FIFO, nothing very exotic in terms of scheduling, right? Data are flowing through the structures. But I think it would have been nice to have some kind of figures about the scheduling of how do you push your data to your board, how you retrieve them. And so you mentioned this in your manuscript, but I would have liked to have a picture to better understand. It's a slide 22. I don't know if you could move to slide 22.
Second.
I had difficulty to understand why. Sorry.
It's there's a big latency between when I push the button and when it actually does something on the screen. So it makes it
yeah, here. So my question is, why does the latency decreases as the batch size increases?
Okay. Yeah. So it's linked with how we, as you said, as we schedule or we push the data in the pipeline and how we measure the latency. So the thing is, what we can do with the ping driver, as it is designed in the way we use it here in Fin, it's that we can push data. So we use the DMA interfaces, and we can push input data and then retrieve these output data after some time. So that's like you give to the input DMA 10 inputs, and then you wait for 10 outputs to be available on the output DMA so you can retrieve it. So this means that when you use only one input, for example, you have a lot of additional latency that is linked to the transfer of data to your pipeline not being completely full. And this is why, for example, with one image, we have a much higher latency than with more than one inputs. And when you increase the batch size, so you increase the number of inputs that you give at one time to the you give to the device, to the design. Sorry, you kind of reach the full potential of the pipeline. You fill your pipeline completely, and you can reach the full potential of the pipeline, and kind of flatten a bit more this initial latency that's linked to the transfer. And
Okay.
also, due to this, it means that the latency is so if I here in the graph I divide it by number of inputs, that's why it decreases. But if you take the runtime latency without normalizing by the number of inputs, obviously it increases with the batch sizes. So we push a certain size of bytes of data, and we compute how much time it took for the data to be sent, processed by the FPGA, and retrieved back. And based on this measure of time, we compute this latency and the throughput.
Oh, so okay, so you somehow averaging things. So because my thinking was, okay, assuming I have a very large batch, the time that goes between the sending of the data and retrieving them would be larger. But okay, I understand the batching thing. It makes more sense now. Thank you. I had a few more questions on the tool on Fin. So the tool Fin. So the features, as I understand, features evolved a lot during the course of your PhD. So you have to, well, actually you contributed to it, but you adapted to it. So my question is more general: is if you had to start this work today, would you still consider Fin, or what would be the alternative? I mean, would the choice be the same today?
I would be inclined to say yes, but I'm so kind of biased because I haven't looked too much into other frameworks for pipeline dataflow architecture. What I can say is that when I started, it was clear that Fin was the best choice in terms of how advanced it was, how much support, how much there was. But I'm not. So another one that I mentioned in the manuscript, also in the slide, is FPGA ConvNet, for example, and I think they've showed interesting results. And it was not very. The project was not. It existed, but it was not very open source when I started the thesis. And I think to this day, there's still less elements that are actually open source. But in terms of pure achievable performances, I don't know how they would compare now to Fin. But I like also the idea of that Fin has built a really large community of contributors and users over the years. And a lot of the contributions and the advancements that are made also come from external users. And I don't find this type of gathered interest in other frameworks. And so I think this is a really good sign that Fin is going to progress forward even further in the future. And it's already a good tool and leads to very efficient implementations. But now that I've seen how far it has progressed throughout my PhD and all the contributions that are made and really where is it going, I think that it's going to be more and more of a relevant choice in the future. But I acknowledge that I'm quite biased in this choice.
Yeah. Okay. Thank you. So one last question about the Fin tool. It's obviously dedicated to the design of neural network in general. Let's say, how much generalizable is it? Let's say I have another data flow oriented application. What could be used in Fin to help me design such such implementation, and how much work would it require to move to a not too far application? I don't know if you know what I mean.
Yeah, I see. well, it's really designed for neural networks. So I would say right off the bat, it would be quite difficult to apply to other types of application or to other type of fields. I'd say the question would be, how easy would it be for you to describe your algorithm as something that would be close to the operations that are used in a neural network? Like if you have a image processing a type of algorithm or field, maybe you can express it in form of image convolutions and things like that. But then if you're going into that direction, you might as well use a neural network to do it in the first place, right? So
yeah, okay,
I wouldn't say that it would be very easy or extremely interesting or relevant to try to use it for another type of application that doesn't use neural networks. Maybe there's a world where it's possible, but I wonder if it would be interesting, or if you would just be better off by using a neural network for your task. Yeah, that would be my answer.
Okay, thank you very much. That's all for me. So let me congratulate you for all the work that you've done. I try to measure the number of hours it takes to provide all these results, this implementation. This is very, very nice work. So thank you.
Okay, thank you, Camille. Thomas, the floor is yours.
Yeah, thank you very much. Thanks for having me. Thanks for this very nice presentation, Hugo. So I'll start a little bit mean, literally. If you go on slide 4, there you just show a very simple formula for the mean IOU. How is it that a mean is just plain sum?
That's right. Thank you for pointing that out. I think I just made a mistake in my slide, that you absolutely need to average it to the number of classes. Otherwise, it's not a mean.
Yeah.
Yeah. Sorry. You're right.
Yeah. Very good. In your thesis, you make the statement that the slow memory that we often have if the memory is external and FPGA platforms pose a limit on the achievable throughput. Under what circumstances is that statement true?
Well, it's true if your design is not computationally bound, meaning that if what limits the throughput is the speed of computations. And I think it's been showed really well into the Fin papers that I'm sure you very well know, where you have like kind of this I would say, I don't exactly remember the names, but you have this curve between, depending on for example, the quantization that you use or the size of the model, at which point it becomes, at which point is it computation bound, and at which point is it memory bound. So it's true. It's true. It depends on the quantization, I would say, or in general case, it depends if it's really the memory itself that is limiting the throughput or the performances of your design, or if it's just the speed of the computations itself.
Well, the issue that I see in this statement is that you're mixing two different things. I mean, the use of the term slow is a little bit ambiguous. I would normally interpret slow as meaning high latency. But the relationship between high latency, let's say high memory readout latency, and throughput is difficult. Right? You can have a high throughput, even though the latency is high, right? It just makes your pipeline longer, the latency. But it could still be the case that you can actually push much work through the pipeline. So, but yeah, please go ahead.
No, I said I agree. So yeah, maybe I did some in the manuscript some confusions between throughput and latency at some point. So there's there's a strict difference. That's also why DPUs or system arrays architecture are able to have a great throughput, although they have a high latency. So I guess I should have been clearer on exactly what I meant by that, but I think the interesting, not just the throughput, but the interesting metric here in the choice of architectures and the choice of having the weights being only on the on-chip memory is mostly the latency more than the throughput itself.
Mm-hmm. Yeah, okay, let's leave it right there. You have made one choice in your experiments. The designs that you tested on the FPGA devices, they do not make use of DSP slices for compute.
Mm-hmm.
Is that a good choice? Would the DSPs potentially offer you more freedom to kind of grow the size of the models or make it faster, whatever? So why did you not use DSP slices?
Okay, yeah, thanks for the question. So I would say it's a timely bound choice in the way that so normally if you have like low bit quantizations, like 4-bit quantization, you can use DSPs to kind of use less loops or balance out a bit the resources, the computation resources that are used. But in general, the DSPs are meant to be to compute on much larger quantization or much larger inputs, and so you're going to be underutilizing. Not utilizing them very correctly, or very not an optimal way. So that's the reason why we didn't choose to go with DSPs, and I think in that particular regard, it probably is easier to implement or to place the design using only LUTs, and but there is scenarios where you can still have make very great use of DSPs. So when you kind of do SCMD where you pack your inputs into larger inputs, like four bits inputs into 116-bit inputs, and then compute the operations in parallel, because then you can do 4 max for multiply accumulate per cycle, and that makes it faster than what you can do with the LUTs, unless you parallelize a lot more. But yeah, no, in general, it's going to be faster than what you can do with the LUTs. So the answer is yes, you can make great use of ESP and make it faster, but you need to have some data packing, and that was not something that was in Fin when I started the thesis, and when I did most of the results that I got here. I know that's something that exists now, and I would be very interested into looking forward to try to change my design and use DSP and see how much they would bring to the overall performance of the design.
Very good, thanks. If we move in this presentation on slide 56, Camille already has taken you there.
Mm-hmm.
And I just want to poke a little bit deeper there. If 56.
Yeah.
What I see on the left hand side and the right hand side respectively. On the left hand side, you have the per time kind of division, both the numerator and the denominator. If you take it out, what it leaves is inference per energy, right? It's essentially the same units, but just the inverse is on the right hand side. So what I would expect is that if I multiply those numbers, violet, orange, green, and blue, that in each of these cases I would get 1,000, but I don't. Where's the gap?
Excellent question. I don't know. What I can tell is that I got the, so on the left hand side on the FPS per watt, the measurement is just the throughput divided by the peak power consumption.
Okay, it's the peak. Okay. That's
the peak. So it doesn't represent the actual power consumption across the whole inference, whereas the energy, it's an integral, right? So I would say the energy per inference is probably more accurate to the actual efficiency than the per watt, because we take the peak watt consumption.
okay. Well, I suppose if you take the peak, it kind of that explains it, right? Because the peak is higher than the average, and then the numbers are a little bit smaller, and then if I multiply them, it's not 1,000, but something below that. Makes complete sense. So there was a question before on estimating the latency, and in your answer, you kind of claimed that shortcuts would pose a challenge in estimating or kind of computing the latency of a network. So that answer kind of lost me a little bit, because I can't picture a scenario where you have data that's taken the shortcut route, essentially just sitting there and waiting to be picked up on the way back. How that adds some kind of complexity to the latency computation to the overall model.
Yeah, no, yeah, you're right. I think it was a bit inaccurate answer. So it doesn't change the latency, provided that you can actually implement the design on the FPGA without losing latency because of a sufficiently sized FIFO. So it doesn't, in theory, it doesn't complicate the computation of the latency, and in the best case scenario where the shortcuts are not a problem for the implementation and this deadlock or these bottlenecks problems, well, you have the same latency as without the shortcuts, but if you only take into account the latency as this sum, nothing gives you, it doesn't give you the, sorry, I'm trying to formulate. You don't know if you're going to actually be able to implement the design and still preserve the throughput and the latency as it is. So it doesn't change the estimation or the computation of the latency. It's just that if you want to not take into account the shortcuts element in your search space when you're doing NAS, you kind of take the assumption that you're going to be able to preserve this latency when you're going to actually be implementing the network on target. And when you have shortcuts, or especially long shortcuts, this assumption is rather difficult to make, I would say. But I agree that my answer was a bit inaccurate in that regard.
Okay. Thanks. I'd be done. Thanks a lot.
Thank you.
Thanks, Thomas. Now, Jacoba, you're on the floor.
Thanks so much. And yeah, thank you, Hugo, for the presentation, and thank you for inviting me. I don't make it very long because I think also most of my questions were already addressed. I would like to ask one question a little bit about the decisions you made for the hardware-oriented neural network design in the end. And I would would ask you to maybe elaborate a little bit more how these decisions influence power.
Power. Oh. Good question. Well, the question is, I think the underlying question is how much the resource usage on the FPGA influence power, and I'm not quite sure about the answer to the question, mainly because if we look at the two different design implementations that I did, like the difference in resource usage between both is not extremely significant. So like it's slightly more, especially LUTs, but like it's not significant. But like the power consumption of the two design is quite different, and that's something I think that I'm not exactly sure why. And so I mean, there's more to just the the resource usage. So I would say I'm not quite really lectured enough into really FPGA architectures or just circuit in general to tell what's the link between hardware, where is the exact link between hardware resource usage and power consumption. So so I don't know. I would say that in general, if you reduce the hardware usage by changing some elements in the design, and reduce the number of computations and the number of parameters, like the state of the memory, you're going to go into the good direction of reducing the power consumption. But I'm not quite sure about the exact relationship between the two. I find it not so evident to me. So yeah, I hope that answers your question.
Okay, thanks, Hugo. Then maybe one very more like an opinion question at the end. So you contributed a lot to the open source world with your work, not only to the Fin tool, but also you published your code as well on GitHub. So I would like to ask you what you think is the key value proposition of open source contributions, and especially in the context of your own work.
So, well, that's a very interesting question. But so I would say in general, the sharing code also is what makes research push forward much faster. I think one of the great aspect and the great success of machine learning and deep learning in general is kind of putting the standard that you have to share your code so that people can reproduce and take over your models and retrain, and that's what makes it especially fast in producing, not the only reason, but it also what makes it very fast into producing new results and new research topics and new improvements in the literature. And so I think that's something that's not very well implanted in the culture of the hardware community in general. Although that it's clear that there is a call for it and that people really like this idea of open science and open source code. I think one of the great success of having open hardware is probably the RISC-V project. So I think there's a lot of value of publishing your code, not just because for the sake of the reproducibility, but also because it gives example of here is how I did to implement my network with Fin and all the things that I added, all the things that I modified, etc. So it gives you an example of the methodology of how you can reproduce with other types of networks, with other works. And for example, one of the things that I used a lot when I tried to learn Fin, and I want to try to implement this ResNet 18 UNet network, is the implementation on the Fin example GitHub of the ResNet 50, where I saw that you could do custom operations and custom steps, and it really gave me the knowledge of the approach of adapting Fin to different networks and new things. So in general, the contribution is that it helps others pick up your work, maybe reproduce a result, but mostly see how they can adapt your approach and to their use cases, to their needs. And if you don't have that, if you just read a paper about an FPGA implementation of a neural network, in general, it's going to be very difficult to try to reproduce the result or just try to follow the same approach, because the amount of details that are given is not enough to, in my opinion, is not enough to be able to pick that up and see if you can adapt it and you can reproduce it with your own use case and your own network. So I tried to keep it short, but it's very wide question. I think a very interesting one, but I could give even more answers to that question, but I'll keep it like this.
All right, thank you, Hugo. I think all my other questions were already addressed, so that's from my side. Thanks.
Okay, thank you, Jacoba. So before I leave the the room for the defense, I will just make one remark and ask you a question. Regarding the measurement of power consumption, I don't know on the board you use, but on some of Xilinx boards, they have this PM bus, which allows to really have an accurate measurement of power, and we used it in order to really be able to extract the power. So you did not have that on your board?
No, one you had was like an INA chip to have a measure of the overall power consumption. So
so
as far as I know, I didn't have access to that. Or maybe I did, but I don't know.
But okay, yes. So this is okay. You were with AMD, so probably they would have told you if this was on the board. And I have a question on slide 30, in fact, which is the question that everybody already had. Excuse me, but it concerns the choices, the modification you made on the INET. How did you choose this modification at first? I mean, once you have them, you can put them in some way and so on and so forth. But here, why did you choose this type of modification to do? And
well, it's based on all that I've learned with implementing the ResNet 18 unit and this type of topologies, where I saw there's a very typical way that, so it's linked to the way that the thin compiler processes the graph, the elements of the graph, and convert them into hardware layers, where you need some association of layers so that it works. For example, you need kind of convolutions to be followed by an activation function, so that they can be merged into the same hardware block. You need things like, it's difficult for the compiler to process branches where there's absolutely nothing on it, which happens very often into ResNet. So that's also why we had to move these activations. Just having this block means that we can, I won't go too much into details because it would be long to explain, but so it's really linked to the experience that I had into implementing ResNet, and I knew that there were elements that
so it's just because it's empirical. You had this experience, and though you had some ideas what to do.
It's empirical and linked also. Some of the layers replacement are also linked to things that were correctly supported by the tool or not, and then I chose to rather go with then the question is, would you rather try to implement them yourself and add them to the tool, or modify the architecture so you can fit with what's there? And since I saw that those modifications were not particularly impactful on the performances, like it was fine, I chose to go in that direction. But I could have said, I want to keep the structure as it is, and then I'm going to modify the tool so that it works. But it's once again, it's a trade-off to find in how much time you want to invest into implementing the network.
Okay, thank you. So, Mathieu, if you want to say a few words.
Thank you, Frédéric. So first of all, I would like to thank the reviewers, so Andrea and Olivier, for their really valuable reviews and feedback on Hugo's work. Also, thank you to all of the members of the jury to have participated in this defense. Thank you, Hugo, for having survived this defense. Okay, so just a few words. Try to be fast also. So 3 years ago, we just asked you if you were motivated to do a PhD. And the idea was to implement semantic segmentation, which is a hard task on FPGAs. And 3 years later, you're showing state-of-the-art results on this. So I think we can call that a mission complete. So your PhD wasn't easy, so you started from scratch. You were the first one to implement a full neural network on FPGA in the team and in the school. So that's important, and it paves the way for a lot of future works in the team, and that's very important. And also with collaborations with AMD, Arcan. We talked about it, but it's really impactful for us. So thank you for that also. we have talked also about open source, and yeah, I just want to emphasize on the fact that it's very important for me, and that's the way that the hardware community should go, and it's not enough the case. So I think you have the same opinion, and I'm happy to share this. Finally, on a more personal stage, I'd like to conclude by saying that you and I are quite different. You tended to open up easily, where I'm sometimes as open as a prison door. You are quite talkative, where I'm concise. You have a tendency to complicate things, and I tend to oversimplify them. So you love metal, and I love music. And yet, I feel that we worked out pretty good together. So I'm very glad for it, and I think we come out having grown, both of us, a lot. So thank you for everything.
Thank you.
Thanks, Mathieu. Mathieu, if you want to close.
Thanks. I think I will say that I totally agree with Mathieu. It's easy for me. And I would also add that we thank a lot AMD team, so Jacoba and Thomas, thanks a lot, because I think that Hugo achieved a lot also because of his stay in AMD Dublin. So it was very important for us to collaborate with you, and I think it was essential for Hugo's success. So thanks again, because I think that this thesis won't have achieved such results without these 6 months in AMD. Thanks a lot to you, Hugo, because you trusted us. You began your PhD thesis during the COVID crisis, and you could have said, "Oh, you're totally crazy, guys! I won't do such a hard task with so hard tools and in such an uncertain context." But you did it. So you trusted us, and I think that's a very important part of you. You are trustful, and you are very courageous when facing very difficult tasks. So thanks again for trusting us and having worked so hard to achieve these wonderful results.
Thank you. Thank you for trusting me as well.
Okay, thank you. So the jury will move to
yes,
deliberate.
And so I sent you another WebEx room for the remote jury.
Okay.
Vous entendez bien? C'est bon?
Ouais.
Yeah, great. So now with the jury got the deliberation, and we wrote down the defense thesis report that I will now read to you. You have presented your work on the co-design of neural network and data flow architecture for segmentation with ease, clarity, and pedagogy. You have answered quite precisely and with a lot of arguments to the numerous questions of the members of the jury. The question have went through the whole set of your work, and the answer that you have given have shown that you were mastering your subject very well, and that you could step back when necessary. You were able to answer both to technical questions, but also to more open questions with ease and very well. We also would like to highlight the fact that you have done a lot of implementation efforts to achieve something that could be measured at the end on the FPGA. And you have also contributed to the film project on you have also contributed to the film project, which is a way to have impact, to give your work a lot of impact. And these works are opening a perspective also at the level of the laboratory here, but also perhaps even further. So for all these reasons, the jury, unanimous, gives you the grade of Dr. DMT Atlantic, Electronic Specialty. Congratulations.
Bravo.
Ça doit être de l'autre côté.
I'll do it in English so all the members of the jury can understand.
Yeah.
So, in the presence of my peers, with the completion of my doctorate in electronics, in my quest for knowledge, I have carried out demanding research, demonstrated intellectual rigor, ethical reflection, and respect for the principles of research integrity. As I pursue my professional career, whatever my chosen field, I pledge to the greatest of my ability to continue to maintain integrity in my relationship to knowledge, in my methods, and in my results.
Oh. Oh.
Thank you very much to all the members of the jury, both in presence and in remote, for attending my defense, for asking such interesting questions and having all this talk and all the time and effort they put into reading and reviewing my work. In particular, I'd like to thank a lot Thomas and Jakova from AMD for the great opportunity they gave me to do this internship at Dublin. So not just them, but also all the researchers, all the employees at AMD that I've been able to, so that I had the opportunity to meet and interact with there. And so it's been, as Matthew said, it was a very great opportunity, and I'm glad that we continued into other contributions after, and I look forward to continuing my work with you. I'd also like to thank my supervisors, Matthew and Mathieu, for their continuous guidance and support, and for just believing in me even in times when I didn't. And so thank you a lot for that. It's been a real pleasure to work under your supervision. Yeah. Then I'd like to thank also all the members of the mathematical engineering department in the school, and also particularly all the members of the Brain team, which I had the chance to work alongside during all these years. It's been I'm forever grateful for all the moments that we shared and all the interesting discussions and fun discussions, and just thank you for all of you for being such nice people to be around with. And so for the last part, I'd like to switch to French. Sorry. So merci beaucoup à tous ceux qui sont venus, merci à mes amis qui ont fait le déplacement, merci à ma famille qui a fait le déplacement et qui me soutiennent dans mes études et tout ça depuis tant d'années sur tellement de niveaux que je pourrais pas tout résumer. Donc merci beaucoup à tous d'être venus. Merci aussi au monde de Darkan d'avoir fait le déplacement aussi pour venir me voir au nom de Paris, etc. Donc voilà, merci beaucoup à tous.
Free our colleagues or remote colleagues.
Thank you very much for your presence.
Yeah, thanks a lot for participating to this jury, and see you soon, I hope. Bye-bye.
Yeah, thank you very much.
Thanks a lot. It was a great cooperation. Thanks,
Great.
Hugo, for your great work.
Thank you.
Yeah, thanks.
Bravo, Hugo.
Invitation and congratulations.
Thank you.
Profite bien du meilleur moment.
Oui. Merci.
À bientôt.
Bientôt. Et oui, pour ceux qui veulent, il y aura un pot pour célébrer